Aaron Murphy and Austin Brown, Marshall University 2020 capstone presentation video. We didn't really have enough time to complete everything. As it stands, we're probably 95% complete. One thing we were missing was our connection between our solenoid valve and our water flow meter. Other than that, there are three other parts. One that holds the main, the front that holds the main bowl there, and then we have two cover pieces that go on. But we could have technically had an operating device had we had just enough time to find a fitting for this and to go to our flow meter, and then of course maybe a couple of days for testing. But anyhow, we will start with the water flow and give a description of how this water is supposed to flow through the device. Right here we have the inlet comes from just a standard water spigot outside, and then this is connected to a solenoid operated valve. The other side comes and supposed to go to the flow meter, and the flow meter will measure the instantaneous flow rate as well as the accumulated flow rate to monitor how much evaporation or your dog has been hydrating with. Then the water will flow through this Y and come down and being monitored by this thermocouple in line with the water flow. Once the water is in the bowl, it will fill up, and once the water level reaches 12.5 inches, the sonar device will tell the Arduino to shut the solenoid valve off. Now, at 12.5 inches, the solenoid will shut off, but if your dog comes in and drinks and the water level drops below 15.5 inches, the sonar device will tell the Arduino to kick the solenoid on, and water will fill the bowl back up to 12.5 inches. 12.5 inches is a rough estimate, which can be adjusted later on in the code. Once we have everything assembled, then we can go in and tweak the code a little bit to get accurate measurements. So the pump is designed to pump the water every 15 or 20 minutes through the water block, and once it goes through the water block, it will come back through and go back into this Y, which will be monitored by the thermocouple. The thermocouple will decide if the temperature is okay. It won't do anything. If the temperature is above 70 degrees, it will tell the H bridge to kick on the TEC module. Now, if the temperature of the water drops below 37, 36 degrees, and all that is adjustable as well within the code, then the Arduino will tell the H bridge to switch the polarity and heat the water to maintain a temperature of around 55 to 65 degrees Fahrenheit. So now we will go on to the electrical portion of the project and give some explanation of that. So we start off right here with a 12 volt 30 amp power supply. It just hooks up to a typical 110 volt receptacle outlet. I have 12 volts coming into this 5 volt power supply, which gives our Arduino Mega power. So then we come in here and we have our Arduino 2560 Mega. We have a PCB board that I soldered together with two buses, one 5 volts and one ground. We have our thermocouple mount and board back here. We also have our temperature and humidity sensor right here. And we allowed, the reason we have the temperature and humidity sensor is to be a more accurate measuring device for our sonar. Our sonar will take into consideration ambient temperature and ambient humidity or relative humidity. That way we can get accurate depth measurements for our water. Right here we have 3 single channel relays, one that will operate our solenoid valve, one that will operate our pump, and one that will operate our fan for our air duct, which is right here. Now these single channel relays are capable of passing 10 amps through the contact tips. It's 5-volt controlled from the Arduino Mega. Right here we have an H bridge, which is it's a motor controller, but we used it for our TEC module because it's a high capacity. Has 4 parallel transistors that will swap the polarity output to the TEC module. So when the thermocouple reads high temperature, the H bridge will cool the water, and then when the water drops below 37-35 degrees Fahrenheit, the polarity will be reversed to the TEC module, therefore heating the water. Our pump is 108 psi that is manually adjustable. Is also pulse width modulated, which we had planned on modulating it down to approximately 3 to 4 volts because it's high capacity. That's probably another thing that we would change if we could, is get a little bit smaller pump. This will work, but the only thing that we didn't really like was the size of the inlet and exit. The size of the inlet and exit of the pump. It was a little bit larger than what we had liked. So the reason that we switched to this one was because of the head loss on the other pumps was just it wasn't a strong enough pump. This is a self-priming pump, whereas the other one was not a self-priming pump. So that was another issue that we had. So if the device was off and the lines were empty, there was no way to initiate that pump process. I would like to turn the attention over here to our little air duct. So right here we have our inlet and outlet going to our water block assembly. You can see the channels inside of the water block. That's for water flow to go through, and underneath that we have our TC module that's mounted right here. It's sandwiched between our water block and our heat sink. So when the TEC module is cooling, the heat will be dissipated on this heat sink, and the fan will draw the heat through the sides and down through the air duct and out the bottom louvers in the base. Now, when the TEC module is heating, there will be no need to remove any heat from the heat sink, so the fan will not come on and the heat will be put through the heat block into the water. Now our TC module is a 15.4 volt maximum with a heat rating of 154 watts. Since we are only putting 12 volts to the TEC module, we have calculated a max Q of 99.48 watts of heat. So with 4 liters per hour pump capacity, we predicted about 29 seconds, 30 seconds of pumping to get a get a water get a bowl of water that is about 70 degrees Fahrenheit down to 55. Again, we didn't really have any testing. This was all just mathematical on paper. So I think that is about it. The fan can also be pulse width modulated, but we wanted max velocity and volume to be able to remove that heat. So we kept it at 12 volts. So if you have any questions or anything, I guess we'll be hearing from you, and I appreciate everyone helping us get this as far as we have. It's been kind of tough this semester, but I will be finishing this on my own and hopefully have a operating device here shortly. All right, Aaron Murphy and Austin Brown signing off. Thank you very much.